Our next speaker is Philippe from Pragmatic Web Security. And I didn't know it was a thing. He's a PhD in web security. Very impressive. Great. And he's going to cover a topic which we already know is extremely popular, and as we can see from all the humanity which is entering our vital space, we know is super popular, which is how to handle security patterns and secrets in the browser. Take it away, Philippe.
All right. Thank you very much for that very kind introduction. Welcome, everyone. Feel free to come a bit forward. You can sit on the ground if you don't mind, so other people can join us. And let's talk about how you can keep secrets or sensitive information in the browser. So if you attended the last talk, Brock said, like, yeah, some people are building these modern applications, spas, where you keep data in the browser, and that's what's actually happening. So what we're going to talk about is this pattern that's happening where you have a browser, you have a backend, and that backend has some sensitive information. What the backend is isn't really important here, because we're going to talk about the browser side. Maybe an API, maybe a web backend, maybe an authorization server sending you tokens. We don't really care about that. What we care about is that there's going to be a request at some point, and the response is going to come back. And that response is going to contain a secret in the header, in the body. Doesn't matter where, it's going to be there. And you want to keep that secret in the browser. I have a very short version of this talk, and it goes like this. Don't do it. The browser is, unfortunately, I've been doing web security for a very long time, and the browser is a very bad place to store sensitive information. But this is a developer track, and we all know if you tell a developer that wants to store information like, yeah, you shouldn't do that, they're going to find a way to do that anyway. That's how things work. That's why we have OAuth flows that handle spas and stuff like that. So I'm going to talk about how you can at least improve the security properties of what you're going to do and the things you need to take into account when moving forward. So first of all, why is this a problem? Why can't you keep stuff in the browser, or why is it challenging? Because a typical web page today contains, let's call it what it is, a lot of crap. There's a lot of stuff going on here. You have user-provided content in here. A restaurant review. Maybe it's a legitimate review, but maybe it contains a little bit of script code that will be executed when you have a cross-site scripting vulnerability. That's not good. You have JavaScript libraries and services. Today we integrate a lot of services into our pages just by adding a snippet of code. Want analytics? Oh yeah, just put this code in there and you're good. And it's going to pull in some extra code and off you go. Potentially dangerous. And you have third-party components. You want to have a chat widget in your support page? Easy. Just find a service that offers that, integrate it, and off you go. Very easy, very nice, but it's all JavaScript. And JavaScript, unfortunately, has some issues. Because the moment one of these things turns malicious, it has access to your web application. It's now running, or there's now running malicious code running in your client-side application in the browser of your user. This is being used to mine cryptocurrency on your machine, which is one of the maybe least harmful side effects. But it's also being used for other real-life attacks. Two examples. There we go. One example is from earlier this year, Fortnite. Fortnite got hacked. I have no idea what Fortnite is or does. I'm that old. But nonetheless, people hacked it through cross-site scripting. And what did they do? They stole access tokens from your account so they could take over your Fortnite account and steal all your virtual whatever stuff you have in there. I don't know what, skins, whatever. I honestly have no idea what the game is. Maybe something I do understand, Ticketmaster. If you want to buy concert tickets, usually you do that through Ticketmaster, at least here in the US. They had a vulnerability as well. Actually, they didn't. Their service providers did. Hackers targeted two of their service providers, installed credit card skimming malware in JavaScript, and it got loaded in the Ticketmaster website, and people stole credit card information. That's because JavaScript code, once it runs, has full access to your application. It can do a lot of things wrong. Hence, storing information in the browser is very challenging. One of the side notes here is I'm not going to talk about preventing these attacks. That would be preventing cross-site scripting or securing your JavaScript dependencies. That's a whole other topic which requires a lot more time to talk about these things. And some of these challenges are even unsolved. I'm going to talk about patterns you can use to make the attack less harmful. I'm going to talk about how you can protect your data a bit better. It's not going to be a silver bullet solution, but it's going to be better than what we are doing in most cases today. So let's start with scenario number one. The first scenario is the most popular one. I can guarantee if somebody here is building browser-based applications that most of you are going to be using this mechanism, and it's called local storage. What you're doing is essentially you have your web application, and it's going to store information in a local storage area. This is provided by the browser. It's a very simple storage API, key value. That simple, very straightforward. The data is in there, and your JavaScript code, that's the little block here, this JavaScript code can now access local storage, store information, read information. Sounds good. How does this work? Well, you see the green stuff on the slide. The green things are origins. Every context in the browser has an origin, which is a scheme, the host, and the port derived from the URL. So you can see here it's HTTPS, restograde.com, and 443, which is from one of my training applications. The local storage area is also isolated per origin. So this origin has one local storage area. That's why the origin is repeated there. All in all, pretty good. This means that this application can read its own data. It could not ever read data from facebook.com from local storage, for example. That simply doesn't work, fortunately. So the browser vendors, when they built the API, thought about that and did a pretty good job there. This is very popular, very easy, very straightforward. Persistent storage. It doesn't get deleted when you close the browser. It just stays there until you manually delete that data. The problem is, however, is that if something goes wrong, if you have your malicious code, your cross-site scripting, or your vulnerable dependency, it also runs in your browser, in your origin. It runs within the application. There's no distinguishing between legitimate and illegitimate code at that point. So when it accesses local storage, it has full access to that data. That's unfortunately a consequence of local storage. And this brings me to the first overview, the first pattern using local storage. It's very easy, very accessible from every page in your browser. But unfortunately, it's not very useful to store sensitive data. My honest recommendation is only use it for long-term storage of non-sensitive data, because there's no way to prevent access once something goes wrong. So what else can you do? Well, local storage has this little brother called session storage. It's the same API, the same spec, and session storage looks very similar on a slide. So you have session storage instead of local storage, and your script code can access it. There's one important difference. Session storage is temporary storage for a set of browsing contexts and origins. So the origin restriction remains, but it's now a set of browsing contexts. So context A has access to session storage A. If it would open a pop-up, window.open, that's considered to be the same set of browsing contexts, so that pop-up has access to the same data. Very easy, very nice. This means if you pop up a window and do something there, you have access to the same store. You can read or write information. However, if something goes wrong in a different window, and that window tries to access some information, it will have access to a different session storage area. Because now it's no longer set A, it belongs to a totally new set B and has access to session storage B in that case. So by doing that, by using session storage, you have some protection, some limitation, because now if the attacker would want to steal information, he would have to ensure that that mistake or that vulnerability exists within the running application in that set of browsing contexts of the user. So it's a bit more secure to use session storage, but it's also a bit less useful because it's only based on the session. The moment you close the windows associated with browsing context A, the storage area is gone. So it's no long-term storage, it's not persistent storage. And that brings us here. So essentially, it's accessible to a set of browsing contexts within an origin, but only for the duration of the lifetime of those browsing contexts. So the moment you close that window or tab in the browser, that information is gone, so it's probably not useful for some scenarios. But it might be useful for storing temporary data. So far, we haven't seen a good solution. So what else can we do? How can we improve on the current state of practice? Well, one way to do that is to use a mechanism that has been in the browser for 20 years. And it's called origin-based isolation, or the same origin policy. Every browser today isolates contexts from each other if they have different origins. So what we do here is we load something in an iframe, for example. And in the iframe, we load something from private.restograde.com or storage.restograde.com or whatever. As long as the origin is different, the browser will isolate these things. There's no direct communication, there's no reaching in, there's no nothing. In that iframe, you can run JavaScript code, you provide that, and that JavaScript code can access a local storage area. So now you can store data in that local storage area, just like before, but in a more isolated fashion. How do you get to that data, or how do you use that data from the legitimate application, from the green outer context? Well, you can send a message to that frame. You can ask the frame to do something for you with that data. And that's essentially the web messaging API. What does this buy you? Well, a very big important difference here is that when the attacker comes around and he can trigger a vulnerability in your application, it's going to be triggered in the actual application running on https restrogate.com 443. So when the vulnerability is exploited and the attacker is running malicious code, he can now access local storage. But not the actual local storage with the data, no, the local storage from that origin which doesn't contain anything useful in this case. And by doing that, we can hide the data from malicious code in our applications. It takes a bit of work, but it's available in all browsers because it has been there for 20 years. The moment they introduced JavaScript, they implemented the same origin policy, enforcing this level of isolation. And that's actually a very important pattern that we can use in a lot of applications today, which we unfortunately do not. Many people don't leverage this mechanism, and that's a bit of a shame in certain cases. All right, this looks pretty good. However, remember what I said in the beginning. The moment malicious code runs, it can do whatever it wants, and there's no way of stopping that once it's running. So the attacker could, in this case, load an iframe from private.restrogate.com and start sending messages to it. And there's no way we can prevent that because cross-site scripting is a much more dangerous problem. The moment you have malicious script code running, it's game over. So remember that. What we're doing here is we're limiting the attack surface. The malicious code still runs, but instead of having raw access to the data, instead of having raw access to this local storage area, it now only has access to the interface our iframe exposes. So the iframe can decide, what are you trying to do? You want to read this information? No, I don't want you to do that. I can perform an operation for you if you want, but I'm not going to give you the raw data. I'm not going to write data. And whatever you see fit for your applications, you can now enforce because the interface is a JavaScript-based interface accepting messages and deciding how to handle those in the application. And this is definitely a big improvement. So what we're doing here is we're using origin-based isolation available in all browsers. And in that origin-based isolation, we can access our data in a more secure way. And this is very useful to store sensitive data for long-term storage, because it's still local storage and it's still persistent. That brings me to the key takeaway. Origin-based isolation is actually really, really, really strong. It's one of the most powerful features we have in browsers today. What we do here is we create an origin without third-party code, without user data. The only piece of data or code we have in there, the only piece of code is storing data, reading data, handling that data and incoming messages. What we expose, that's up to us. We can decide what kind of operations we want to expose. Maybe it's read information, write information, maybe it's certain operations on the data, maybe it's sending a request to a backend with a token. We can choose how we want to implement those operations. And the third point is maybe the most important one. Whenever you get an incoming message, the browser will tell us where did that message come from. Oh, it came from restrogate.com. Yeah, we trust those guys, so I'm going to do this. If it comes from evil.com, you'll have to make a decision. Do you want to trust that, yes or no? Well, it depends on what you're building, but probably not. So you can, at that point, you can decide like, hey, a request coming from evil.com to do something with this information. No, I'm not going to do that. And this is one of the ways to store data more securely. I'm not done. Not yet. It's one key takeaway. There's one thing we haven't looked at yet, and that is how does the browser handle storing this data? Because the local storage API is very easy. Local storage.setItem. Doesn't get any simpler than that. Key value. But what happens behind the scenes? There's a reason this is a screenshot from Firefox, because Firefox is a browser that is fairly easy to analyze how they handle things. So what I did is I looked at where Firefox stores this data. And if you look closer, you can go to your Firefox profile and you find a webappstore.sqlite file stored in there. And a SQLite is basically a SQL database in a file. It's a pretty easy format, so you can connect to the file and then start querying the contents of that file. And you can see here the green line at the bottom shows you, it's a bit weird because it's backwards, but essentially it shows you the secret and the treasure key value being stored in that database. And this means that if somebody has access to that file, they have access to all the stored information. But since we're trying to store sensitive information, that's probably not the best scenario to be in. Because what we have now is we have our very secure origin-based isolation to store data, our exposed interface, and now the attacker, once he gets access to your disk, he can easily grab everything that's in there. If you're storing non-sensitive stuff in there, it might not be relevant, but if you're storing personal information, a local cache of data, healthcare information, financial stuff, you might want to protect that against unauthorized access. So in the second part, I want to look at how we can do that. How can we secure that data? How can we make sure that if the attacker can read it, he can't do anything useful with it? You see where this is going, right? We can encrypt the data. Awesome. Data encryption. Well, actually, in browsers today, it's not that hard because we have the Web Crypto API, which actually handles encryption, which is pretty good, and decryption as well. What do we need for that? We need a key. We need that key to encrypt the data when we store it, and we need that key to decrypt the data when we read it. Keep in mind, we have this origin-based isolation technique. The key itself is also isolated in that private origin. There's no way to read the key, there's no way to steal the key unless something goes wrong in that origin. But how do we get the key? Two options. Option number one is getting the key from the server. So in this scenario, we have our little iframe, we have our code there. Our code can request this key from a backend, from your server-side application. Of course, it's going to be an authorized request, not an anonymous one. It's going to carry some authentication information, whether it's a token or a cookie. I'll leave that up to the previous talk on how to deal with these things. But essentially, you're going to get a user-specific key, best even a device-specific key from the backend. And when you get that key, you can load that into your Web Crypto API, you can initialize that, and from that point on, you can use that key to encrypt and decrypt data in the browser. This is, again, a very, I wouldn't say straightforward, because the code is actually pretty ugly to do that, but it's a very elegant mechanism to store data in local storage without it being compromised through disk-based access. Server-provided key, very useful in an online scenario. Very useful if your application is always online, you can easily get the key and start using it. However, if you want to store some data in the browser and you want to use it in an offline fashion, this is not going to work very well. Because if I bootstrap the application offline, I open it on my mobile phone, for example, there's no key, there's no data access. Because without the key, you cannot decrypt data already stored there. So there's a second pattern you can use, and that involves the user. As a user, I can't remember cryptographic keys. Well, passwords are hard enough as it is, so for the love of God, don't start remembering very long keys. But there's a mechanism you can use, and that's using a password and turn that into a cryptographic key. So we can ask, in an offline fashion, we can ask the user, can I get your application password? And when we get the password, we can again use the Web Crypto API to turn that single password, that short password, usually into a long cryptographic key. That's called key stretching. You can essentially stretch out the password using black magic crypto, and afterwards out comes a cryptographic key you can use for crypto operations, encryption, decryption. Sorry, this was supposed to be there. So now we have the key, and now we can use it as before with our Web Crypto API to actually encrypt our data in our local storage container. Again, works pretty well, and works in an offline fashion because you have linked this to the user's password. You could tie this into the login form, for example, so it works in an online mode. It's very transparent. The user logs in, and you grab the password to generate the key in the background. And in offline mode, you can prompt the user like, hey, you appear to be offline. If you want to access your locally stored data, just give us your password so we can decrypt that data before using it. And that's essentially encryption with a password-derived key. The key here, or the algorithm you use, is called key stretching. And that's essentially what we are using. Web Crypto API has implementations for that. And that brings me to the real takeaway here. The browser is not a place to store secrets. Try to remember that. If you can avoid storing data in the browser, please do so. We have seen that with the previous talk talked about refresh tokens in the browser, that it's a very bad idea. It's a very common sense thing to do. And one of the patterns that emerges in the OAuth world is called backend for frontend, where you have like a server-side component to handle your tokens, and then you use your frontend just to handle the data instead of handling these tokens. That's a very common sense mechanism to do. Sometimes you do want to store data. Doesn't matter what it is. If you need to do that, if it's sensitive, consider using this dedicated origin. It's going to be a little bit more work to set this up apart from using local storage, but it's going to be worth it in the end because it reduces the attack surface of your application significantly when something goes wrong. And then finally, consider encrypting the data if it's really sensitive, if it's PII information stored on the device for a long time. I recommend trying to encrypt it, which makes a lot of sense in modern browsers. All right. I know this was maybe a lot of information, a lot of high-level information with fancy PowerPoint pictures. Don't worry, I've built code examples for that. So if you go to this website, you can actually find the slides there. You can find code examples, both running live and the repo on GitHub. So you can look at how this is implemented, look at how the web crypto APIs are implemented, which is too dirty to put on a slide, but you can figure out how that works. And there's also a cheat sheet available that gives a nice overview of these patterns, which you can share with your colleagues, friends, and other developers to help them understand the differences between all of these patterns, the pros and cons, and to help you make your decision for your application. All right, thank you very much. The talks are also linked on Twitter, by the way. And if there are any questions, I'd be happy to answer them right now or after the talk in the hallway as well.
Thank you. Question on the pattern where you are retrieving the encryption key from the back end. What's preventing malware from doing the same thing?
What do you define malware?
So from the site. From the site, different origin?
Yeah, so it depends. Essentially, you fall back on authorization like always. So if there's code running in a legitimate application and it's going to make that request, it will have to mimic your authorization as you would have from within the private origin. So the code normally launches this from within the private origin. If it's going to be an XHR request, there's going to be cores in there, and the browser is going to tell the server, I'm coming from this origin. And the backend can decide, like, anything that's not private@restofgate.com, I don't want that.
Okay, so you can leverage that same isolation to protect the authentication
it's
cred.
basically API authorization decisions in the backend.
Hi, thanks. So you mentioned the importance or the significance of cross-site scripting, and that seems to me that that's the most resonant thing here is that if you have a cross-site scripting vulnerability, and say you're storing tokens, like access tokens, and those are being used to access resource server APIs, well, once you've gotten a cross-site scripting problem, it's true this would prevent exfiltration, but it doesn't really prevent those tokens from being used in the same exact way that the application would legitimately use them. So you're just as vulnerable with, even if you do all the steps you just listed, if you have a cross-site scripting error,
yes.
Aren't you just as vulnerable?
I wouldn't say just as vulnerable, but yes, the problem is still significant. That's why I mentioned that once you have XSS, it's essentially game over.
Right,
It just depends on how screwed you are when the game is over. So yes, you're absolutely right. Cross-site scripting is extremely dangerous. And the moment malicious code runs in the application, it can do whatever the legitimate application can do. And there's no distinguishing from that. But we have moved the problem from raw data access, as in do whatever you want, to limited access as according to the rules of our API. And that's essentially what we're doing. So it's not a silver bullet solution, but for example, if you're storing sensitive information in the browser, it can prevent a total compromise through an unrelated page. One good example is often error pages have XSS vulnerabilities. Error pages have nothing to do with the application. It's like a generic catch-all, oh crap, we didn't find this page, 404, and there's a cross-site scripting in there, which can affect everything your application would do. And in this case, it would have limited to no impact. So that's essentially what we're trying to achieve here. But I agree, cross-site scripting remains a main problem, and you should heavily invest in preventing XSS, as hard as that may be in today's landscape. All right.
Hi, I was actually just curious if you heard of a bug that I'm kind of running into, which actually I'm really excited that this is the pattern that you have, because this is exactly what we're gunning for. But Safari, of course, we have an issue where we load the iframe onto our trusted origin, but we have like a subdomain where we want to store the local storage. Safari treats that as temporal data. And so it works fine on Chrome, Firefox, everything like that, but Safari will actually clear out the local storage because it was brought in by an iframe. I don't know if you've heard of that issue.
I haven't. It's probably part of their tracking protection, I assume.
It's pretty new.
I would have to look into that, because first of all, that's a violation of what the spec says that local storage is supposed to be.
Yep.
But I have no good answer, except I have to look into that, and that might be a problem, yeah, for sure.
Okay. Anybody from Apple here? Just kidding.
We have time for one last question. Anyone? All right. No one.
All right. Thank you very much.
It was brilliant.